You've heard about functions before, but it's important for you to start to really understand what it means for a relationship to be a function. I remember memorizing rules about how to tell if something was a function or not, and not really understanding it. So I want you to think about a mailman, and his job is to deliver letters. So he goes to the first person, and he gives her a letter, and she's happy. He goes to the second person, gives him a letter, and he's happy too. But then the strangest thing happens. His third envelope actually has two different names on it, and they don't live together. They live in separate houses. So what happens if our mailman tries to take one letter and deliver it to two people? Well, if he rips it in half, they sure are not going to be happy about it. So that is a problem. So our rule for this mailman to do his job correctly is that he delivers one letter to one mailbox. If he does that, we're good. But if he tries to take one letter and deliver it to two mailboxes, or more even, not a good idea. Now, what happens if he gets another letter and delivers it back to one of those original people? Is that okay? Sure, he could give her as many letters as he wants, as long as he doesn't try to take one letter and give it to two separate people. So, two letters to one mailbox. Okay, that's good too. So keep this picture in your brain as you're thinking about functions, about whether or not you're going to have some unhappy people. Each of these letters is like the input of a function, and each of the mailboxes is like the output. Let's go into our notes. Okay, so here's our mailman, and he is getting his envelopes. They are going into our little function machine. They are going out, and he's delivering them to mailboxes. So the rule to be a function is that each envelope can only be delivered to one mailbox. So in our next picture, each of our envelopes are numbered 3, 7, 1, and 0, and each of our mailboxes 5, 9, 3, and 2 are also numbered. Now, by making a chart, this is a way to keep track of which letter or which envelope gets delivered to each mailbox. So 3 got delivered to 5, 7 got delivered to 9, 1 got delivered to 3, and 0 got delivered to 2. So based on this definition, each envelope was only delivered to one mailbox. But like I said before, those envelopes are really the input values, and those mailboxes are really the output values. So our rule for this to be a function is that each input can only have one output. Okay, let's try our next one, see if it's a function or not. We have envelopes labeled 5, 6, and -3. Here's who they're being delivered to. So let's look at our chart. 5 was delivered to mailbox 4. 6 was delivered to mailbox 1. 3 was delivered to -2. Sorry, -3 to -2. But now we have a problem, because here this is our chart telling us to deliver envelope 6 to mailbox -5, but envelope 6 was already delivered. We're trying to send one envelope to two different people. So is this a function? No. But I do want you to get a little bit more specific and give me the reason. The input 6 has two different outputs. 1 and -5. Go through these 3 examples on your own by pushing pause. Alright, let's see what we have here. Is this a function? Yes. Each input has only one output. Now these 4s might throw you off, but remember, it doesn't matter if a certain mailbox gets many letters, and that's what's happening here. Envelope 2 went to mailbox 4, envelope 5 went to mailbox 4, 11 went to 4, and 18 went to 4. So mailbox 4 was just very popular and got lots of mail this day, and that's okay. Over here, if you look at your x's, each of these points gives you a relationship. And we see here that 5 got delivered to 2 different outputs. So this is not a function. What about here? Well, you might be able to tell just by looking at the chart, but if not, you could put each point here. So -2, -5, +2, +1, +4, -4, and +5, +3. And by looking at this, we can verify, yes, each input only has one output. So this is also a function. And remember to give me reasons here as well. A couple vocabulary words for you. If you take a box and put all of your inputs in one box, it gets a special name, domain. So the definition for a domain is all of the input values. And then if you collect all of your outputs in one box, that box could be labeled as the range. So our definition here, all of the output values. There's a few different ways we can look at it. If you have your numbers in a table, all of the x's, well, those are our inputs, so this is your domain. And then all of the y's are your range. So our domain would be a list of numbers, like that. And our range would also be a list of numbers. Example 9 gives us these 3 points, and they're asking for the range, which means we only need the outputs. 1, -3, and 0. This time they're only looking for the domain, so the inputs are all we need. So again, you could go through and list out each point if you like. Otherwise, here the x value is -4. Here it's -2, -1, and 4 would be the domain for this set of numbers. Okay, so we've covered domain and we've covered range. Now let's go over some new notation that applies to functions. Instead of using x and y's, we could use x for the input and change the y into f of x for an output. What this allows us to do is show right away that a given equation is a function. So by writing f of x equals 1 minus x squared, I'm saying, hey, guess what? Each input for this equation has only one output. So here we have g of x equals -x squared plus 4x plus 1. They want us to find each function value. That means we are given an input and they want us to find the output. Also notice Up here, our function notation used an F. Here it used a G. That doesn't matter. This letter could be anything you want. A lot of times we'll use F, we'll use G, we'll use H. Those are really the most common ones. Okay, so what we need to do is we need to replace the X with the number that we see here. So in this case, they're asking us to plug in a 2. So everywhere I see an X, I'm going to put it there. And just a suggestion, a strong suggestion, when you plug in numbers, I suggest putting parentheses around it. It'll help you keep your math straight. So we have negative 2 squared plus 4 times 2 plus 1. So here the exponent is only on the 2. Negative 4 plus 8 plus 1. So that is 4 plus 1, which gives us 5. Try B on your own. Here, they're asking us to plug in t. So even though it's not a number, we can still replace each of our x values with a t. Negative t squared plus 4 times t plus 1. And then you want to simplify. So here we have t squared with a negative in front plus 4t plus 1. And in this last one, x plus 2 is what they would like to plug in. Now again, don't get thrown off. Even though the variable that they used before was an x, we are going to take this x out and replace it with x plus 2. So we end up with negative x plus 2 squared plus 4 x plus 2 plus 1. So we are going to have some work to simplify this. X plus 2 squared, we have to FOIL. We end up with x squared plus 4x plus 4. I'm running out of room here, so I'm going to continue it on the next line. Plus 4x plus 8 plus 1. And now we need to distribute the negative. And now we have negative 4x plus 4x is 0. 8 minus 4 is 4 plus 1. And that is our answer for this problem.